Hello, seniors. Today we're going to continue with the topic we started yesterday, electronic assignment 12, motion in a line. We're going to see the second part where we're going to involve the concept of acceleration to a real life problem, right? So if you remember, yesterday we have seen example 18 where we discussed this concept basically, where the derivative of the displacement function gives us the velocity function. Remember the sign rules, right? If we talk about positive displacement or positive velocity, we're talking about being at an initial position to the right or having a positive velocity, which means that the object is moving to the right or up, right? And if we talk about negative position, we could say we say that the object is either to the left or down with respect to the origin. And if the velocity is negative, it means that the object is moving to the left or down depending on the situation. Okay, so we're gonna scroll down to this example where we're gonna discuss how acceleration also is also analyzed through the concept of calculus. So it says a particle moves along a line with a displacement function, and we get negative t cubed plus 12t squared minus 36t plus 20 in meters for 0 to 8 seconds. So part A says, write an expression for the velocity and acceleration of the particle at time t. Okay, so we already know how to find the velocity. We know that if we differentiate the displacement function, we're going to get the velocity function, okay? So the velocity function is, in this case, negative 3t squared plus 24t minus 36. This is our velocity function. And if we want to find the acceleration function, we just need to find the second derivative of the displacement function. So we're going to say that it is equal to s prime prime of t, which is the same as saying v prime of t, the first derivative of velocity. So if I differentiate this expression again, we're going to get negative 6t plus 24. And this is the acceleration function. I forgot to write that. I'm going to displace this a little bit. So this is equal to acceleration with respect to time. And it is equal to negative 6t plus 24. Okay, so that's the expression for both velocity and acceleration of this particle for any time t. Okay, let's go to part B, where it says find the initial position, velocity, and acceleration for the particle. Okay, so the word initial implies time equals 0, right? So up to here, it's easy, right? We need to find s of 0, the initial position, s of 0, which in this case would be negative 0 cubed plus 12 times 0 squared minus 36 times 0 plus 20. And this gives us that the initial position of the particle is 20 meters. That means that the particle is to the right of the origin at the beginning of its motion. Then initial velocity would be v0, so it's negative 3 times 0 squared plus 24 times 0 minus 36. So we get that the initial velocity is negative 36. We're talking about meters per second, meters per second here. We get a negative value, that means that the object is moving to the left, right? So I'm going to write this here. Initially to the right of the origin. That's what that value tells us. And this value, negative 36, means that initially moving to the left. Moving to the left. And what about the initial acceleration? To find the initial acceleration, we do the same thing, but with the acceleration function, a of 0, and this is negative 6 times 0 plus 24, and we get a value of positive 24. Acceleration is measured in meters per second squared, okay? So a positive value for acceleration means that although the object is moving to the left, it is braking, right? The velocity is decreasing, and it is trying to change its direction, right? So I'm gonna write velocity decreasing. It is trying to move to the left. So velocity is decreasing as signs are different, right? So are different. And we're gonna say that the object is trying to move to the right. It's like when we're in a car and we brake, right? Although we're moving forward, by braking, we're decreasing the velocity, and the acceleration or the deceleration is in the opposite direction, okay? Before we continue with the problem, I forgot to read this theory up here. It says, the instantaneous rate of change of velocity is the acceleration function, okay? So here it is explained that the acceleration, at, is the derivative of velocity, or we could also say that it is the second derivative of displacement, okay? And here's a rule that you need to understand. When the acceleration is positive, that means greater than 0, the velocity of the object is increasing. When the acceleration is negative, the velocity of the object is decreasing. And for acceleration equals 0, the velocity is constant. If there is no acceleration, we're talking about constant velocity, okay? Then it says, speed is the absolute value of velocity. Velocity tells us how fast an object is moving and the direction in which it is moving. Speed tells us only how fast it is moving. To determine if an object in motion is speeding up or slowing down, you can compare the signs of velocity and acceleration. When velocity and acceleration have the same sign, the object motion is speeding up, right? And when velocity and acceleration have different signs, the object in motion is slowing down. And that's exactly what we had here, right? In this scenario, the initial velocity and initial acceleration, we get different signs. That means that the object in motion is slowing down, okay? So here's just a mathematical representation of speed. It's the absolute value of velocity. That means that it is always positive whenever you read the word speed. This is something that you should have seen in physics as well. Okay, so let's continue now with the problem. We're gonna go to part C. Part C, which says the following. Find when the particle changes direction for 0 to 8 seconds. Then find intervals on which the particle travels right and left. Okay, so here we have two clue words. Changes direction. If you remember from last class, changing direction occurs when the velocity of the object is 0, right? We're going to call this like a critical point. When the object is at rest, well, imagine an object is moving to the right, then it comes to rest, and then it moves left, right? So whenever it comes to rest, it means that it is changing its direction, okay? So basically what we need to do to find when the particle changes direction is we need to set the velocity function, we need to set that to 0, okay? So let me write that down. Changing direction implies that we need to set the velocity function to 0. Okay, so that's exactly what we're going to do. We're going to set this equation to 0. 0 is equal to negative 3t squared plus 24t minus 36. And then we need to solve for this. I see that we can take out a common factor of negative 3 here, negative 3. So we're going to get t squared minus 8t and plus 12. Plus 12. We can take the negative 3 dividing to the other side and it will simplify because 0 divided by negative 3 is still 0. So 0 is equal to t squared minus 8t plus 12, right? So then we can solve this. We can apply case 5, multiply, add. A pair of values that multiply would give me positive 12 and added would give me negative 8. That pair of values in this case is negative 6 and negative 2, right? T minus 6 and t minus 2. That means that the first time in which the object is at rest is at 2 seconds. And the second time in which the object is at rest is at 6 seconds. Okay? If okay, so that's the first part where we're asked to find when the particle changes direction. So we get two values for 2 seconds and for 6 seconds. Both of those values are inside the interval. Okay, so the second part is the interesting part. It says, then find intervals on which the particle travels right and left. Okay? If you realize from the problem, we have found already the initial velocity, which is a negative value. That means that the object is initially moving to the left, right? And that means that it is moving to the left until 2 seconds. At 2 seconds, the velocity is 0. So between 2 seconds and 6 seconds, the object changes direction and is moving right. And then after 6 seconds, again, the object will be moving to the left. Okay? I'm going to show you how to graphically interpret what I just explained. Okay? So I'm going to make a graph here of velocity with respect to time, okay? And then I'm gonna compare this with the acceleration function so you can understand this clearly. So I'm gonna make this like this. This is velocity with respect to time. This is time, okay? So I'm gonna change this should go to negative values as well. I'm gonna make this a little bit shorter. Just a second. I'm gonna move this up. There. I'm gonna change this to black. There. Okay, so this is velocity with respect to time. If I make a graph of how velocity is working, the first thing I need to write down are these two critical values where velocity is 0, right? So let's assume that, for example, 2 is somewhere around here. I'm going to make it a little bit more. So 2 is maybe somewhere around here. 4 would be somewhere around here. I'm just writing 4, and then 6 would be here, right? So 2 and 6 are my critical points. I know for sure that for these two values, my velocity is equal to 0, right? So I'm gonna mark these 2 points because velocity is 0 for those 2 points, okay? And I know that the initial velocity is negative 36. That means that when my time is 0, then my velocity is negative 36. So I'm gonna assume that, for example, this value is negative 36, okay? So this is the initial velocity of this object, okay? If you realize what I'm getting here, and if you look at the equation that we found for velocity, you would see that this is a quadratic function, right? It's a parabola, which is a sad phase, right? Because the coefficient in front of the t squared is a negative value. That means that if you see these 3 points we have here, this 2 and this one, you can clearly make a sketch of the parabola, right? And at time equals 4, we would get a maximum value of the velocity, which I'm gonna do it just there. I don't care about the value yet, but I'm gonna make the sketch to make this look like a parabola. So this looks something like this, okay? Something like this. I'm just doing a sketch for you to understand. So here it is it's easy to visualize how the object is moving. Whenever the velocity is negative, that is for all this interval over here, from here to here, from that interval, my velocity is a negative value. That means that the object is moving to the left for all that interval, right? Then from 2 seconds to 6 seconds, my velocity is positive. It's a positive value, right? So from 2 to 6, the object is moving to the right because the velocity is positive, right? And then from 6 and forward, we're only analyzing this problem until 8 seconds, but it actually keeps on increasing. It keeps on going down until infinity. The object is moving again to the left, okay? So you see how these 2 points are my critical points, because those are the points where my velocity is 0. And those are the points which mark a change in direction of the object, okay? So we already answered this. The intervals on which the particle travels right and left, we can say that from 0, this is 0, right? From 0 to 2, the object is moving left. From 2 to 6, it is moving right. And from 6 forward, it is moving to the left, okay? Let's move on to part D. It says, find when acceleration is 0 for 0 to 8 seconds. Then find the intervals on which the particle is speeding up and slowing down. Okay, so we need to find when the acceleration is 0. That means that we need to set the acceleration function to 0, right? So that's exactly what we're going to do. The acceleration function is this one over here. So we're going to say that 0 is equal to negative 6t plus 24. And we're going to solve for t. We're going to find the time when acceleration is 0. So this is basically, if we take it to the other side, this would be time is equal to 24 divided by 6, and that's 4 seconds. That means that at 4 seconds, the acceleration of this object is equal to 0. Okay, so we already found this. And then it says, then find the intervals on which the particle is speeding up and slowing down. Okay, so just as we did with velocity, I'm going to make a graph of the acceleration. If you take a look at the function, we said that for velocity, the function was a quadratic function, right? But for the acceleration, what type of function is this? This is a linear function, right? We have negative 6t plus 24. If you remember from the equation y equals mx plus c, m is the slope, right? So negative 6 is a slope. That means that this line is going down, right? It's decreasing because the slope is negative. And the y-intercept is positive 24. It's a positive value. That means that it begins with a positive value, right? So we're going to make a sketch of this just to see what is happening, and we're going to relate it to the graph of velocity. So just as we did for velocity, we're going to make the graph for acceleration. We're going to do something like this. Let's see if I can make it fit here. There. And we're going to make it here. Something like this. Okay, so once again, this is time and this is acceleration now. Okay, we're making an acceleration with respect to time graph. Okay, so we know for sure from our equation that positive 24 is our initial acceleration, which is what we got here as well. So 0 and 24, I'm going to say that this value over here is 24. This is at a known point of the line, right? And we could say that, for example, at time equals 4, I'm going to respect this same sketch. You see that 4 is in the same position here. At time equals 4 seconds, the acceleration is also 0. So here we have 2 given points of the line, and since we have already 2 points, that's more than enough in order to be able to graph the line, right? So this is the equation of acceleration with respect to time for this particular object, okay? So what do you see here? You see that from 0, this is time 0, from 0 to 4 seconds, we say that the object has a positive acceleration, right? So I'm going to write this as, let me think about. So from 0, we say that there's a positive acceleration. And from, let me see if I can make this fit better. Nope. There, maybe this 4. So here we have 4, right? 4. So positive acceleration. I'm going to change this down here. Positive acceleration. And from 4 up to 8, or up to the last value, we have already a negative acceleration because we're below the y-axis, right? So this is a negative acceleration. Negative acceleration. And for time equals 4, we know that the acceleration is 0, okay? So from this analysis, if you compare both graphs, we would say that, let me bring this down like this. I'm going to make like cuts here, 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 and this one right here. If you see, from 0 to 2 seconds, my velocity was negative, right? But my acceleration was positive, right? So I'm gonna make this like this. This is negative velocity, but my acceleration is positive. That means that from the interval from 0 to 2 seconds, I'm gonna write 2 here and 6 here. If we have different signs, then this means that the object is slowing down, right? So I'm gonna make like a small chart here where I'm gonna say time interval, then velocity, acceleration, and conclusion, okay? So I'm going to repeat the analysis here for you to understand this clearly. There. From the time interval we're analyzing, from 0 to 2 seconds, from 0 to 2 seconds. Our velocity has a negative sign, right? So I'm going to write this as negative. And my acceleration has a positive sign. So if they have different signs, we conclude that the object is slowing down, right? When they have different signs, we're talking about slowing down. Then the second interval is from 2 to 4 seconds. From 2 to 4 seconds, and I'm going to use a different color here, my velocity is positive, and my acceleration is also positive for that same interval, right? Sorry, positive, not negative. There you go, positive. So from 2 to 4 seconds, velocity is positive, and acceleration is also positive. That means that for that interval, from 2 to 4 seconds, the object is speeding up. Then if we analyze, let me do this with maybe purple. From 4 to 6 seconds, my velocity is positive, and my acceleration is negative here, right? It's a negative value. So from 4 to 6 seconds, velocity is positive, but my acceleration is negative. That means that the object is slowing down. Slowing down. Finally, for the last interval, I see that, let me do this with, let's use brown. My velocity is a negative value, and my acceleration is also a negative value. So for the last part, from 6 seconds to 8 seconds, velocity is negative, acceleration is negative. So as both have the same sign, the object is speeding up. Speeding up, but towards the left, right? In this case, it's speeding up towards, right? Speeding up towards the right, and in this case, it's speeding up towards the left. Okay, so one last thing I wanted to analyze. As I brought this graph analysis that we're going to be seeing a lot in later classes, this is what I wanted to analyze. These are all the different types of motions that you can see in physics or in math or whatever you see this. It's commonly seen in physics, right? D is displacement, V is velocity, A is acceleration. So remember that for the following graphs. Look at the first case. In the first case, we see that displacement is a linear function, right? It's increasing as time passes, okay? Time is always in the x-axis, okay? It's always displacement over time, velocity over time, acceleration over time, okay? So if I have this situation in which the displacement is increasing as time goes by, but increasing in a constant way, then we're talking about constant velocity and no acceleration. You see that in this case, acceleration is always equal to 0, right? So there's no acceleration, but that means that there's a constant velocity, and because there's a constant velocity, the displacement or distance is increasing in a steady way, okay? So that's called a constant positive velocity. Another scenario is, for example, this one. Let's analyze it from the acceleration. In this case, we have a constant acceleration which is different from 0, okay? Let's assume that, for example, this is 5, okay? So there is a value for the acceleration, but that value is constant. It's a horizontal line. If this occurs, then that means that the velocity will be increasing through time, right? As I have acceleration, then velocity changes and it is increasing. And if the velocity is changing throughout time, that means that my displacement will have this shape. It will be like an exponential function, right? It will be increasing more and more each time because the object, let's suppose a car, is accelerating, right? So this is called increasing positive velocity. Then we have, for example, this case in which you see that the acceleration is always 0, but we start with an initial velocity, with a constant initial velocity because there's no acceleration, and then the object suddenly breaks and velocity is decreased to 0, right? In this interval, we have 0 velocity. So if that occurs, that means that the displacement increases for this first interval, but then it remains constant. The object does not move anymore for this second interval, okay? I hope you're understanding this because this is pretty interesting. Let's see this case. This is called constant positive velocity or rest, okay? Then we have this case in which there appears to be an acceleration, a constant acceleration at the beginning, but then there's no acceleration. So you see that initially velocity is increasing, but then when there's no acceleration, velocity remains constant. And that kind of combines these two situations, right? We first increase the displacement exponentially, and then when there's no acceleration, the displacement increases as a linear function. That is called increasing positive velocity / constant positive velocity. Then we have, okay, this is the same as we just saw, same as above. Then we have this case, for example, which is similar to what we just solved in the example. It says, imagine you have a constant but negative acceleration. This is a negative acceleration because we're below the y-axis, right? So my velocity, if we start with a positive velocity, velocity will go decreasing with time because we're applying brakes, for example. We're applying a constant negative acceleration. So velocity is decreasing with time. That means that the displacement initially will go to the right because my velocity is positive, but then I will reach a value in which after that my velocity becomes negative, so the displacement of the object starts decreasing. That means that it is going back to the left. Okay? So that's a situation of decreasing positive velocity / increasing negative velocity. And well, then we have this case, which is very similar to what we just saw. So we can skip this one. And then we have this one in which we combine all of the different situations. First, positive acceleration, then no acceleration, then negative acceleration. So you see that velocity first increases, then it remains constant because there's no acceleration, and then it decreases because I'm braking, right? My acceleration is negative. So how does that look for the displacement? We first increase exponentially, then we increase steadily like a line, and then it goes decreasing, has a decreasing trend because my velocity goes decreasing through time, okay? So that's how we analyze this. And you see how all of the graphs of displacement, velocity, and acceleration are interrelated, right? They are all connected. And one thing that it's very important for you to notice is that always the displacement, well, if we start with the acceleration, it's the simplest function, right? In this case, it's a horizontal line. Then the velocity function, it's a little bit more complex. It's still a line, but it has a slope, right? It is not slope 0 like in this case. And then this one has one increasing order again. Instead of being a line, it's already a quadratic function, okay? So that's something that we're going to be covering in the future live sessions, but that's something you should know, that whenever we're increasing from acceleration to velocity and then to displacement, we are increasing the order of the function, and that is clearly visible in the exercise we just did. If you take a look at this, the acceleration is just a simple line function. Then velocity is a quadratic function. You see the order. This is to the power of 1. This is to the power of 2. And then the displacement formula is to the power of 3. Okay, so we're increasing the degree or the order of the function as we go up in the pyramid, we will call it. Okay, so that's something very important that you should be able to recognize already. So I hope this was clear. If not, please let me know. We're going to cover these doubts in future live sessions. See you.